Hello, my name is Ashwarya Pillai. In this video on reduction potentials, you are going to learn how to predict which species is more likely to be reduced using reduction potential tables. This is an important skill because when you're called upon to write a full balanced equation including both the oxidation half reaction and the reduction half reaction, rather than being told what is being oxidized and reduced, you will be expected to determine that using a reduction potential table. But before we jump into that, I want you to understand what a reduction potential is. Basically, it tells you how likely a chemical species is to acquire electrons and therefore be reduced. So, going back to the homework example from Learning Objective 1, if I say that gaining homework is like reduction because it decreases my social lifetime, then the class where I'm likely to get the most homework would have the greatest reduction potential. It's important to note that the reduction potential is dependent on concentration, temperature, and pressure, and that the standard electric potential is measured at a concentration of 1 molar, a pressure of 1 atmosphere, and a temperature of 25 degrees Celsius. We do this because measuring reduction potentials at these values is our way of measuring them in a controlled environment, allowing us to compare them against each other in our reduction potential table. Also remember that in order to standardize something, we have to compare it against a specific designated value, kind of like how you zero a weighing scale after you've added your measuring bowl but before you add any of the stuff you're actually measuring. Again, we do this because it allows the measured values of different chemical species to be compared against each other in a reduction potential table. Therefore, a larger, more positive reduction potential indicates that the chemical species is more likely to be reduced. So, looking at our table, we can say, for example, that because palladium has a larger, more positive reduction potential than, say, lead, palladium is more likely to be reduced than is lead. The only difference between the oxidation potential and the reduction potential of a chemical species is the sign, so the quantity stays the same. So going off our previous example, if we were to flip the signs, going off of our previous example, if we were to flip the signs of the reduction potentials for palladium, we would get a standard oxidation potential of negative 0.987 volts. Similarly, if we were to the only difference between the oxidation potential and the reduction potential of a chemical species is the sign, so the quantity stays the same. So going off of our previous example, if we were to flip the sign of the reduction potential for palladium, we would get an oxidation potential of negative 0.987 volts. Similarly, if we were to switch the sign of the reduction potential for lead, we get an oxidation potential of 0.126 volts. Thus, since a more positive oxidation potential means more likely to be oxidized, we can determine that lead is more likely to be oxidized than palladium. Let's give this a try with a couple more examples. The question asks you to rank the species from most likely to be reduced to least likely to be reduced. So begin by identifying the reduction potential of each species. We can use the reduction potential table to find the reduction potentials of nickel, sodium, cobalt, strontium, silver, and tin. To make things easier, I've written them out here. Since we know that larger and more positive means more likely to be reduced, we can go ahead and order the values from highest to lowest to get the following. Replacing these with their associated molecules reveals our answer. Being able to identify which chemical species is most likely to be reduced using a reduction potential table is an important step in being able to generate the overall ionic equation for a redox reaction. So spend some time getting familiar with reduction potential tables and how to use them.